A storm is loading across the central United States right now, and the number of people inside the warning zone keeps climbing. 40 million Americans from Oklahoma up through Minnesota are sitting under a forecast that federal meteorologists have been rewriting all week. Very large hail, damaging winds, a few tornadoes, and this is one pulse in a season that already holds records no one wanted. We will show you the invisible wall where these storms are born, the warm Gulf water feeding them, the jet stream that refuses to move, and the one corridor the atmosphere keeps hitting again. If this kind of breakdown is useful, take a second to subscribe. It genuinely helps. The storm is closer than the forecast suggests. Let's begin. A line of thunderstorms is organizing across the central United States tonight, and the warning polygon keeps growing. What started as a scattered risk zone 2 days ago now stretches from northern Oklahoma up through southern Minnesota. Inside that polygon sit roughly 40 million people, and the federal forecasters watching it have already rewritten the outlook 3 times this week. The agency doing the watching is the Storm Prediction Center in Norman, Oklahoma. They are the quiet nerve center of American severe weather. Every thunderstorm risk you have ever heard about on the news started as a hand-drawn polygon in their office. When they raise the risk level, insurance companies move, emergency managers call in staff, pilots reroute. The polygon matters. Right now, that polygon is flashing with a specific combination that makes meteorologists pay close attention. Large hail, damaging straight-line winds, and what the forecast discussion calls a few tornadoes, particularly during the early stages of storm development. That phrase sounds calm. It is not calm. Translated into plain language, it means this. The first storms that fire this afternoon, when the air is hottest and the atmosphere is most charged, are the ones most likely to spin. After those first hours, the storms tend to merge into a long line that races east. The line itself can still do damage, but the deadliest window is the first one, when individual storms stand alone on the map, pulling in moisture and wind and turning like a slow top. The ingredients driving this are sitting in plain sight on the weather models. A deep pocket of cold, low-pressure air is anchored over the western United States. In front of it, across the plains, warm and humid air has been pouring north out of the Gulf of Mexico. Where those two air masses meet, the atmosphere does what it always does. It tries to mix them, violently. That is the engine of every severe storm you've ever seen on television. Here is the part that most headlines miss. This is not one storm appearing out of nowhere. This system is the next pulse in a pattern that has been firing the same corridor for weeks. Across 2026, the Storm Prediction Center has already issued an unusually high number of days at enhanced risk, which is level 3 on a scale that only goes to 5. For context, an average year through late April might see 4 to 8 such days in a given region. Parts of the Midwest have already seen 15. Something about the atmosphere this spring is stuck. The current forecast calls for storms to ignite in the late afternoon, grow upscale into bowing segments overnight, and push east-southeast into the overnight hours on a strong low-level jet. That last detail matters more than it sounds. A strong low-level jet means the winds close to the ground are screaming at highway speeds, feeding the storms like a constant intravenous drip. Storms with that kind of feed do not weaken after dark. They often get worse. And that is where the real danger for sleeping people begins. The polygon you're looking at on the news tonight is not the full story. It is the visible edge of a larger pattern, one that has already surprised the people whose job is to predict it. To understand why this keeps happening, and why 40 million is almost certainly an undercount of what is truly exposed, we have to look at the scale the meteorologists actually use, because most people have been reading it wrong. There are 5 risk levels on the Storm Prediction Center's scale, and the one everyone underestimates is the second. Level 1 is marginal, Level 2 is slight, Level 3 is enhanced, Level 4 is moderate, Level 5 is high. Those words sound like they climb gently. They do not. The jump between each level is not linear, it is closer to exponential. A slight risk, the word that sounds almost harmless, statistically covers the zone where most tornadoes in the United States actually happen. Because slight risk areas are huge, they cover vast stretches of land where people live and sleep. A high risk, by contrast, is rare. Forecasters issue only a handful in any given year. When they do, it usually means hospitals start pre-staging ambulances. This is where the polygon language becomes life or death. Most Americans living inside a slight risk today will hear the word slight and go to bed. The word sounds like a shrug. But the storm that flattened Lena, Illinois last week started inside a risk zone that was not at the top of the scale either. The storm that killed people in Michigan earlier this year developed inside a marginal risk, which is level 1. No tornado watch was ever issued before it struck. The words on the map are calibrated for the atmosphere, not for your nerves. Here is the mechanism behind why the scale acts this way. The upgrades between levels are driven by 2 ingredients: coverage and intensity. Coverage means how much of the area is likely to see severe weather. Intensity means how strong those storms can get. A slight risk usually means scattered storms of normal severe strength. An enhanced risk means numerous storms, and the ones that form are more likely to become intense. A moderate risk means widespread severe storms with a real chance of strong tornadoes. A high risk means the atmosphere is primed to produce a destructive long-track outbreak. The line between slight and enhanced is where the season of 2026 keeps landing. That detail matters because enhanced risk days used to be uncommon for most of the country. This year, forecast offices across the Midwest have been logging them at a rate that forecasters are openly calling unusual. The Chicago office noted that its area has already been inside severe weather outlooks on 15 different days so far this year, an unusual number of which were at enhanced or higher. That same office has issued 128 severe thunderstorm and tornado warnings so far this year. That is a record through this date, a record that the season is still adding to. There is a second thing viewers tend to miss. The scale only forecasts the probability of severe weather. It does not forecast where a specific tornado will go. A slight risk over your neighbourhood does not mean nothing will happen there. It means the odds are lower than in the darker zones on the map. The polygon cannot see your house. You have to. That distinction has killed people. The forecast polygon you're inside tonight was upgraded twice before it reached its current shape. Each upgrade was triggered by data the forecasters were watching in real time. Temperatures, dew points, wind shear, and one specific measurement they kept circling on the map. It points to a corridor the atmosphere refuses to leave alone. The storm track tonight runs almost in a straight line from northern Oklahoma up into southern Minnesota. 800 miles of alert boxes stacked like dominoes waiting to fall. This corridor is not random. It is drawn by the atmosphere itself. Look at the ingredients from above. A long-wave trough sits anchored over the western United States. Cold, dry air spills down the eastern side of the Rocky Mountains. Warm, humid air flows north out of the Gulf of Mexico. Those two air masses do not blend. They collide along a north-south boundary that runs straight through the middle of the country. That boundary is where tonight's polygon lives. Every city inside that line is sitting inside what meteorologists call a warm sector. A warm sector is the most volatile real estate in American weather. It is the zone south of a cold front and east of a dry line, where the air is warm, moist, and unstable. It is the zone where the country grows most of its severe weather. Oklahoma City is inside it tonight. Wichita is inside it. Kansas City, Des Moines, and Minneapolis are all exposed depending on how far north the warm air surges. The reason this corridor keeps getting hit is the shape of the atmosphere above it. The jet stream, that fast river of wind 6 miles up, has dug a sharp trough into the western states. Air spinning around that trough accelerates as it rounds the base, launching a stream of strong winds northeastward across the plains. That upper-level push acts like a vacuum cleaner. It sucks air upward from the ground, and when the rising air is humid and warm, it condenses into towering thunderstorms that can reach 60,000 feet. That is why the same map keeps lighting up. The corridor has a name in meteorology. Forecasters sometimes call it the severe weather belt. Historically, the center of it ran through the southern plains, mostly Texas, Oklahoma, and Kansas. Tonight's corridor reaches much further north than that. Southern Minnesota is not a place people think of for severe thunderstorms in late April. But the warm sector stretching there right now has dew points in the mid-60s. That is Gulf of Mexico moisture reaching the Canadian border. And this matters for one specific reason. When warm, moist air pushes unusually far north in April, it meets air that is still cold from winter. The temperature contrast across short distances becomes steep. Steep contrast means sharp boundaries. Sharp boundaries mean strong lift. And strong lift, with the right wind pattern above, means storms that rotate. Rotating storms are the ones that produce tornadoes. There is one more feature hiding inside this corridor that most newscasts skip. The cities along it are not evenly spaced. There are pockets of high population density and pockets of sparse farmland. A tornado touching down in a cornfield becomes a number in a database. The same tornado touching down in a suburb of Des Moines or Minneapolis becomes a disaster. The storms do not choose, only the geography does. That geography has quietly been shifting, because the real center of America's severe weather risk is no longer where most people still think it is. The corridor has been moving, and the place it has moved toward is a state that now leads the entire country in tornadoes, hail reports, and damaging winds this year. That state is not in the southern plains. The storm tonight is not an isolated event. It is the next pulse of a pattern that has already rewritten the 2026 record book. As of the middle of April, the National Weather Service office in Chicago had issued 128 severe thunderstorm and tornado warnings this year alone. That is a record through this date for that office. 8 severe thunderstorm watches, 6 tornado watches, 20 confirmed tornadoes inside its forecast area. Those numbers are not supposed to arrive this early in the spring. Back up for a moment. The severe weather season in the United States typically climbs through March, peaks in mid to late May, and then tapers into summer. The early part of April is usually a transition period. Warm air is still winning its fight against winter. Outbreaks happen, but they tend to be local. The big multi-state events are usually still a few weeks away. This year broke that timeline. On April 17th, a single outbreak across the central United States produced 46 tornadoes in one event. The Storm Prediction Center had warned of it days in advance, raising parts of Iowa, Illinois, Wisconsin, and Minnesota into elevated tornado risk zones. When the storms fired, they produced what forecasters had warned about. A high-end EF2 tornado tore through southern Rochester, Minnesota. Another high-end EF2 shredded the town of Lena, Illinois. A 41-year-old man in Wisconsin was killed by lightning during the storms. One outbreak, 46 tornadoes, multiple towns reshaped, and the bigger number underneath those statistics is the one worth understanding. Long-range forecasters from AccuWeather had predicted the 2026 United States tornado total to land between 1,050 and 1,250. The historical average is around 1,225. The prior year, 2025, ran hot with 1,544 reports. This year was supposed to cool off. Instead, the atmosphere has delivered a front-loaded season, with an unusually dense concentration of outbreaks along a corridor that stretches from the southern plains up into the Great Lakes. Forecasters have been honest about what they do not yet know, but they have also been direct about what they do see. This spring, the pattern is stuck. The same air masses keep colliding in the same places, and when the atmosphere repeats itself, the map repeats with it. That is why tonight's storm matters beyond tonight. It is not just one warning. It is the next entry in a run-in tally that the forecast offices themselves are calling unusual. The Chicago office used the phrase "very active start" in an official public summary. The Storm Prediction Center has outlooked their forecast area for severe weather 15 different days already, an unusual number of those at enhanced risk or higher. Typical years through this date see 4 to 8, 3 to 4 times the normal rate. When a season starts like this, forecasters watch two things. One is whether the pattern breaks. The other is whether a major metropolitan area finally ends up inside the wrong polygon at the wrong time. So far in 2026, the big hits have landed in small towns. Lena, Rochester, Crawford County. Each of those places has fewer than 50,000 residents. That is partly luck and partly geography. Luck runs out, and the next chapter of this pattern is already visible on the map. One state is absorbing most of it. A state that now leads the country in a category no one expected it to. Illinois is leading the United States in tornado reports, hail reports, and damaging wind reports this year, by a wide margin in all three. Through April 19th, Illinois had logged 80 tornado reports. The second-place state, Mississippi, had 43. That is almost double. Illinois had 147 hail reports. Iowa sat next to it with 143. And Illinois had topped the wind report rankings with 245, ahead of Alabama with 209. That combination, leading in all three categories simultaneously, is almost unheard of in April. To understand why that is so strange, remember the traditional geography. Tornado Alley has historically run through the southern and central plains, Oklahoma, Kansas, Texas, Nebraska. Those states dominated the rankings for decades. A secondary zone known informally as Dixie Alley ran through Mississippi, Alabama, and parts of Tennessee, with its own deadly reputation. Illinois was never the headline state. It got hit, yes, but it was not the leader. This year, that map has rearranged itself. The cause is a mix of pattern and geography. The jet stream has dug its trough further west this spring, which pushes the main storm track further east at ground level. The warm, moist Gulf air has been surging north up the Mississippi River Valley, and the cold fronts rolling out of the Rockies have been firing their severe weather a day or two later than usual, which means the storms hit their peak intensity right as they reach Illinois, Iowa, and Indiana. In other words, the state is catching storms that have had time to mature. That timing matters. A supercell that fires in western Kansas at mid-afternoon needs several hours to reach full strength. By the time it crosses into Illinois that evening, it is often at its most dangerous. And Illinois sits in a landscape with no protective terrain. It is flat, open, heavily populated, and dotted with small towns that are difficult to warn in time. The April 17th outbreak hit that state the hardest. 27 confirmed tornadoes touched down in Illinois during that single event. A tornado outbreak that spanned from Oklahoma to Wisconsin dropped at least 48 tornadoes total, and more than half of them landed on Illinois soil. 2 house fires broke out near Chicago when the storm system rolled through. A town called Lena in Stephenson County took a direct hit from a high-end EF2 that the sheriff's office asked the public to stay away from entirely. The damage surveys are still ongoing. The forecasters who track this data for a living have used the word remarkable to describe the pattern. The Chicago office called the corridor from eastern Iowa into southern Wisconsin and northern Illinois remarkably active. That is restrained language from people who spend their careers being restrained. When they call something remarkable, you pay attention. What is happening in Illinois this year may be a preview of what is happening to the whole map. Severe weather risk is not fixed. The atmosphere does not respect old rankings, and the storm pressing east tonight will hit some of the same ground that has already been hit this month. Because one of the towns Illinois lost earlier this month is still pulling itself out of the wreckage, and what happened there in under 5 minutes is the kind of event that defines a season. On April 17th, a tornado walked into the town of Lena, Illinois, and changed the place in less time than it takes to boil water for pasta. It was a high-end EF2. On the scale forecasters use to measure tornado strength, EF2 sites in the middle, above weak and below violent. High-end means it was at the top of its category, with winds somewhere between 125 and 135 miles per hour. That is fast enough to strip roofs off houses, fast enough to lift vehicles, fast enough to turn small flying debris into projectiles that can cut through drywall. Lena has a population of around 2,800 people. The Stephenson County Sheriff's Office asked the public to avoid the town entirely after the tornado passed. That request is not common. Emergency services typically open roads as quickly as they can. A full public avoidance request means the damage was so widespread and the power lines and gas infrastructure so compromised that even curious drivers could get hurt. Photographs and aerial surveys in the hours that followed showed what that meant on the ground. Roofs were ripped entirely off homes, walls collapsed inward, trees snapped at the trunk, not just debranched. Aerial video from above the town showed the kind of damage footprint meteorologists use to confirm tornado intensity. A continuous track of destruction, a few hundred yards wide that cut through the town like a curved blade. The mechanism behind that kind of damage is worth understanding. An EF2 tornado is not just a strong wind, it is a rotating column of air where the wind speeds at the edges can differ by more than 100 miles an hour from one side of the funnel to the other. That difference creates enormous pressure gradients. Houses do not fail from pure wind. They fail because one side of the structure is pulled while the other side is pushed, usually at the same moment. The roof goes first. Once the roof goes, the walls lose their bracing, and the building unzips. Most people inside do not have time to react. Lena residents had a tornado warning before the storm hit, because this is the United States, and the warning system worked that afternoon. The Storm Prediction Center had issued a moderate risk of severe weather for that region. Radar operators had been tracking the parent supercell for an hour before it dropped the tornado. Sirens sounded, phones alerted, And even with all of that, minutes is all you get. Here is the detail most viewers miss. From the moment a tornado forms to the moment it reaches a specific address, the typical lead time in the United States is around 13 minutes. For weaker storms, it can be less. For nighttime storms hidden in rain, it can be 0. 13 minutes is enough time to get to a basement or an interior room if you are awake, if you hear the warning, and if you act immediately. Lena is a daytime event that most people survived because they heard it coming. But the same storm system that hit Lena also moved through parts of the country at night. And the night tornado problem is a completely separate kind of danger, one that kills people at rates several times higher than daytime storms. Because the warning system assumes one very important thing that is not always true. It assumes you are awake to receive it. The reason the atmosphere over Kansas is behaving this way starts 3,000 miles to the west, in the surface waters of the equatorial Pacific Ocean. That ocean has been running cold, not dramatically, but measurably, for the better part of 3 years. Meteorologists call this pattern La Niña. It is the cool phase of a larger climate cycle, known by its technical name, the El Niño Southern Oscillation, and it has been steering the weather of North America in ways most people never see. This spring, that pattern is collapsing. Oceanographers watching subsurface data in the tropical Pacific have been tracking a warm water wave moving eastward along the equator. It is called a Kelvin wave, and it is essentially a pulse of heat travelling through the deep ocean. That warm water is now starting to surface in the eastern Pacific. Combined with weakening trade winds, the signs are clear. The ocean is pivoting from its cool phase back toward neutral, and forecasters expect El Niño conditions to develop later in 2026. But here is what matters for tonight's storm. During a La Niña spring, the jet stream across North America tends to sit further north than average. That northward shift does two things. It keeps the Pacific Northwest and the northern plains active with storm systems, and it pulls the clash zone between cold and warm air further into the heart of the continent. Meteorologists have studied this pattern for decades. Research going back to before the last major El Niño found that La Niña springs often produce more instability, more wind shear in the critical layers of the atmosphere, and a slightly earlier peak in severe weather activity. Tornado seasons during La Niña years have been shown to run hotter than the historical average, with some years producing activity well above 100% of normal. The 2011 spring, one of the deadliest tornado seasons on record, came during a strong La Niña. This is not a theory, it is a pattern observed across many decades of data. And 2026 is a La Niña that is not quite letting go. Even as the ocean warms, the atmosphere is lagging. The jet stream is still behaving as if the cool phase were in full force. That means the configuration that favors severe weather in the central United States is still locked in, even though the ocean underneath it has started to shift. That lag is why forecasters cannot simply point at one ingredient and claim certainty. They can say what the ocean is doing, they can say what the jet stream is doing, they can show the historical correlation between La Niña and more active severe weather. What they cannot do is promise that tonight's tornado hits a specific town. The connection between Pacific waters and a funnel cloud over Iowa is real, but it operates through layers of atmospheric machinery. Each of those layers is a separate amplifier. The ocean nudges the jet stream positions the trough drives the fronts collide with Gulf moisture. The collision fires the storms, and the storms, if the wind profile above them is right, begin to rotate. Pull out any one link in that chain, and the storm might still happen, just weaker. keep all the links in place, and the result is what the country has been watching unfold on radar this spring. There is one more piece that makes 2026 unusual. The El Niño coming later this year is projected to arrive fast. That kind of rapid pivot can temporarily over-energize the atmosphere during the transition. The jet stream becomes unstable, it buckles more sharply, it digs deeper troughs, which brings us to the piece directly above the storms tonight. The jet stream is the single most important feature of the atmosphere above you right now, and it has been stuck in almost the same position for weeks. It is a ribbon of fast-moving air about 6 to 9 miles above the surface, where the temperature of the planet shifts from warm tropics to cold pole. That temperature contrast drives a river of wind that can reach 200 miles per hour at its core. The jet stream does not run in a straight line. It waves, it dips, it climbs. Every wave it makes steers the weather below it. This spring the wave pattern has locked into place. A deep trough of the jet stream has carved a U-shape over the western United States. Air circulating around that trough accelerates as it turns the corner at the bottom and launches northeast across the plains. That pattern keeps firing the same corridor. Cold air spills south from Canada along the western flank. Warm air pulls north up the Gulf Coast along the eastern flank. They meet in the middle, repeatedly. The technical word for this is a blocking pattern. A blocking pattern is when atmospheric systems refuse to move east at their usual pace. They stall. Weeks of weather happen over the same regions. Drought worsens in one area, flooding builds in another, and in the case of severe weather, the same warm sector gets loaded, fired and reloaded day after day. The Storm Prediction Center has noted the persistence of this pattern in their outlook discussions. Their longer-range forecasts have repeatedly described what they call an active severe weather pattern that is expected to continue through early next week and beyond. That kind of language, repeated across multiple forecast cycles, is forecaster shorthand for a jet stream that will not budge. Why it will not budge is the harder question. Scientists have proposed several mechanisms, and the honest answer is that some are well established and others are still debated. What is well established is this. When a large temperature contrast locks into a particular geography, the jet stream tends to follow that contrast. Right now, the western United States has unusually cold air aloft. The Gulf of Mexico is unusually warm. The gap between the two is sharper than usual, and sharp gaps produce strong, stable waves. There is another factor in the background. The loss of Arctic sea ice has been a topic of active research in recent years, with studies suggesting it may be contributing to more frequent blocking patterns in the Northern Hemisphere. That research is not settled, and reasonable scientists disagree about how large the effect is. But the observation that the jet stream has been behaving strangely more often is not in dispute. Whatever the deeper cause, the near-term consequence is direct. A stuck jet stream means the ingredients for severe weather keep showing up in the same places. Forecasters cannot tell a town in Oklahoma to relax just because it was hit last week. Under a blocking pattern, the same town is often in the crosshairs again within days. This is the mechanism that has produced the front-loaded season meteorologists have been describing. It is why Illinois leads the country in tornado reports. It is why the Chicago Forecast Office has set a warning record. And it is why tonight's polygon is drawn where it is drawn. The storms are not wandering. They are being aimed. And what they are being aimed at is a supply of fuel unusually rich for this early in the year. That fuel is rising north out of a body of water most Americans never connect to their local thunderstorm. It is warmer than it should be right now, and it is feeding everything above it. Every severe thunderstorm you see tonight owes its existence to water, evaporating off the Gulf of Mexico. That sentence sounds simple, its consequences are not. The Gulf is the engine room of American severe weather. It sits directly south of the continent's severe weather corridor, and its surface waters release huge volumes of warm, moist air into the lower atmosphere year-round. That moisture is what forecasters mean when they talk about fuel. Without it, storms cannot reach severe strength. The measurement meteorologists care about most is the dew point. Dew point is the temperature at which air becomes saturated with moisture. A dew point in the 30s is dry air. A dew point in the 50s is moderately humid. A dew point in the 60s or above is the kind of thick, heavy, oppressive air you can feel on your skin. That upper 60s air is the signature of Gulf moisture, and it is the signature of dangerous, severe weather. Tonight, mid-60s dew points are being pulled north across much of the central United States. Forecast discussions from the Storm Prediction Center this week have repeatedly called out the low-level jet pushing those mid-60-degree dew points far north across the warm front. That matters because the air at lower levels, the first mile or so off the ground, is what feeds into the base of a thunderstorm. A storm pulling in dry air at its base will struggle. A storm pulling in saturated, Gulf-conditioned air will explode upward. Those explosions are what produce severe weather. When warm, moist air rises, it cools. When it cools past its dew point, the moisture condenses into cloud droplets. Condensation releases heat. That released heat warms the surrounding air. Warmer air rises faster. The process self-amplifies. A storm that starts as a small cumulus cloud can, within 30 minutes, tower to 60,000 feet if the supply of moisture at its base is rich enough. Picture a chimney pulling air upward. The hotter the fire at the bottom, the stronger the draft. The Gulf of Mexico is the fire. This year that fire is hotter than usual. Surface waters across much of the Gulf have been running warmer than historical averages for several seasons now. Warmer water evaporates more efficiently. More evaporation means more moisture in the air above it. More moisture means higher dew points reaching further inland. And higher dew points reaching further inland mean the severe weather corridor can extend further north than it used to. Meteorologists have been watching this signal for years. The research on sea surface temperatures across the Gulf is one of the cleaner datasets in climate science. The water is warmer. Whether that is driven primarily by long-term climate change, by a particular ocean current cycle, or by some combination of both, is still being studied. What is not debated is the observation itself. The thermometer does not lie, and the atmosphere above the Gulf responds to the water underneath it. That response is showing up in tonight's forecast. Computer models have been projecting unstable air masses, pushing well north of where April usually sees them. Some parts of Minnesota are about to experience dew points that used to belong in Oklahoma in May. That shift does not guarantee tornadoes. It guarantees the potential. It loads the gun. What pulls the trigger is the collision zone where the moisture meets its opposite. That collision zone has a specific geography. It is not a line on a weather map. It is an invisible wall that moves across the central United States every spring. Most Americans have never heard its name. Storm chasers build their entire careers around it, and it is where tonight's severe weather is most likely to begin. Somewhere across West Texas and the Oklahoma Panhandle right now, an invisible wall is sliding east across the plains. It is called the dry line, and if you could see it, you would see a strip of air where the humidity drops by half in the span of a few miles. West of the line, the air is dry and hot, pouring off the high deserts of the southwestern United States. East of the line, the air is warm and soaked, pulled north out of the Gulf of Mexico. Between them, a sharp boundary where the two refuse to blend. That boundary is one of the most reliable storm factories in the world. The dry line is not a weather front in the usual sense. A cold front is a temperature boundary. A warm front is another temperature boundary. The dry line is a moisture boundary. The temperatures on either side may be similar. What differs is how much water vapor each air mass is carrying. The difference is enough to ignite thunderstorms. Here is the mechanism. During the day, the ground across Texas and Oklahoma heats up rapidly under the spring sun. The dry air to the west heats up faster than the moist air to the east, because water vapor takes more energy to warm. That uneven heating creates a push. The dry hot air surges east. The moist air gets lifted, and where moist air gets lifted past its dew point, storms begin to form. This is why so many severe weather forecasts focus on a specific line of longitude on the map. Storm chasers know the dry line intimately. They position themselves on its eastern side in the late afternoon, sometimes for hours, watching a completely cloudless sky. Then, almost on schedule, a small puff of cumulus appears. Within 30 minutes, it is a towering storm. Within an hour, it can be a supercell with a rotating wall cloud. The dry line does not announce itself, it simply delivers. In 2026, forecasters have noted that the dry line has been particularly sharp. The contrast between the dry air flowing east out of the desert and the moist Gulf air flowing north has been stronger than typical. Some of that is the El Niño transition. Some is the warmer Gulf surface waters. Some is the persistent jet stream pattern above. All three combine into a dry line that fires storms efficiently. Tonight, as the warm sector loads across the central plains, forecasters will be watching the dry line's position closely. If it reaches far enough east before the sunset cools the atmosphere, it can fire discrete supercells. Those are the most dangerous kind of storm because they stand alone on the map, pulling in the full supply of warm, moist air without competition. Supercells produce most of the strong tornadoes in the United States. If the dry line fires late, the storms tend to merge into a line. That line is still dangerous. It produces damaging winds and sometimes embedded tornadoes, especially the short-lived kind that drop quickly from bowing segments. But it is less likely to produce the long-track, violent tornadoes that reshape entire towns. The timing of the dry line, therefore, often determines the character of the night. There is one more detail that makes the dry line such a fascinating piece of meteorology. It is nearly invisible on regular satellite and surface maps. You cannot see it the way you can see a cold front. Forecasters track it by combining dew point readings, satellite moisture imagery, and the subtle cumulus field that forms along its eastern edge. Only in the radar loops once the storms start firing does the dry line become obvious. By then, the decisions that matter have already been made, because the storms born along that invisible wall do not simply rise straight up and dissipate. They spin, they organize, they turn into the rotating engines that produce the country's worst tornadoes. And what makes them spin is a feature of the wind that most viewers have heard about, but few have ever really understood. The reason a thunderstorm can become a tornado factory has almost nothing to do with the wind you feel on the ground. It has everything to do with the wind a mile above you, the wind 3 miles above you, and the wind 6 miles above you, and whether all three are pointing in different directions. That mismatch is called wind shear. It is the single most important ingredient in tornado formation, and it is the one that most weather forecasts handle the worst when trying to explain it to the public. Here is the simple version. Imagine you are holding a hot dog horizontally between your palms. If you push your right hand forward and your left hand backward, the hot dog starts to roll. That rolling motion is invisible in the air above a thunderstorm. Winds near the ground might be moving south to north. Winds a few thousand feet up might be moving southwest to northeast. Winds higher still might be screaming west to east. Different directions, different speeds, stacked on top of each other. The atmosphere rolls. Normally, that rolling tube of spinning air stays horizontal, invisible, and harmless. It takes a thunderstorm to do something with it. When a thunderstorm forms and begins drawing warm, moist air upward at its base, it can tilt that horizontal rolling tube vertically. Suddenly, what was a harmless, invisible roll becomes a vertical column of spinning air inside the storm. Meteorologists call that a mesocyclone. It is typically a few miles wide. It is usually invisible unless you can see the whole storm from a distance and watch the entire thunderhead slowly rotating like a top. A mesocyclone is not yet a tornado, but it is the cradle in which tornadoes form. Inside that rotation, smaller and smaller vortices can tighten, like a figure skater pulling their arms in during a spin. When the rotation concentrates down to a few hundred yards wide, reaches the ground, and connects the cloud base to the surface, you have a tornado. Every stage of that process depends on wind shear above the storm. Forecasters measure shear in two main ways. One is the difference in wind direction and speed from the ground up to about 3 miles. That is called low-level shear, and it is particularly important for tornado formation. The other is the difference from the ground up to about 6 miles. That is called deep layer shear, and it is important for organizing supercells and keeping them alive for hours. Tonight's forecast is watching both. The Storm Prediction Center discussion for the region has flagged effective layer shear around 40 knots. That is a specific number with a specific meaning. 40 knots is around 46 miles per hour of directional change across the depth of the storm. That is enough to support supercell thunderstorms, the discrete rotating variety that produce most strong tornadoes. Below that number, storms tend to be weaker. Above it, they tend to become monsters. 40 knots is not a monster value. It is solidly in the range where dangerous storms form. It is the number at which forecasters start adding specific language about tornado potential into their outlooks. And it is a key piece of why tonight's polygon was drawn with the size it was. Wind shear alone is not enough to produce a tornado. It needs a partner. That partner is instability, the raw amount of energy available in the atmosphere for storms to explode upward. The measurement for that is a number most viewers see on weather graphics without understanding what they are looking at. It is a number tonight's forecast has circled in bold. The most important number on tonight's forecast is a measurement that almost no one outside meteorology understands. It is called CAPE. The letters stand for Convective Available Potential Energy. In plain language, it is how much fuel the atmosphere has loaded into the column above a specific location. The higher the CAPE, the more explosive the storms can become once they form. The number forecasters are watching tonight is between 2,000 and 3,000 joules per kilogram. Here is what that actually means. Think of the atmosphere as a vertical column of air stretching from the surface to the top of the troposphere, about 8 miles up. Somewhere in that column, warm air near the ground is trying to rise because it is less dense than the cold air above it. CAPE measures how much room that rising air has to accelerate before it runs into something that stops it. More CAPE equals a longer runway equals a faster vertical rocket. A CAPE value of 500 is weak. Storms that form under it may produce some rain and a lightning strike or two. A CAPE value of 1,000 is moderate, enough for the occasional severe thunderstorm. A CAPE value of 2,000 is high. 3,000 is very high. Anything above 4,000 is considered extreme, and those values sometimes appear during the most dangerous outbreaks in American history. The upper 4,000 range has been recorded during some of the most infamous tornado days on record. Tonight's forecast of 2,000 to 3,000 joules per kilogram places the region in the high range. Not historic, not record, but more than enough. That much energy means the storms that form will have the runway they need to reach the top of the troposphere, where their anvils can spread out for hundreds of miles. The higher a storm climbs, the more dangerous it tends to become. That is because the top of a storm acts as a thermodynamic engine. Warm, moist air enters at the base. It rises. It releases its heat through condensation. It exhausts at the top. Cool, dry air sinks back down the outside edges. The faster that cycle spins, the more organized the storm becomes. At very high Cape values, storms develop an updraft so strong that they can suspend hailstones the size of softballs for 10 or 15 minutes before the stones grow too heavy and fall. 10 minutes of suspension is why some hail reaches the sizes it does. Earlier this year, Illinois experienced what became a state record large hail event, with stones measured at more than 6 inches in diameter. That number is worth pausing on. 6 inches wide is roughly the size of a softball. A stone that large falling at terminal velocity can reach speeds approaching 100 miles per hour when it strikes the ground. It can punch through a car roof. It can kill livestock. It can injure or kill a person standing unprotected in the open. The physics that produce 6-inch hail are the same physics scaled up: high Cape, strong wind shear, a persistent updraft. Add enough of each, and a storm can grow hail that in another era would have seemed impossible. Tonight's numbers are not quite that extreme, but they are high enough that forecasters are preparing for the full menu of severe weather hazards: very large hail, damaging straight-line winds, and, where the wind profiles align just right, tornadoes. What kind of tornadoes depends on what kind of storms form, and storms do not all look the same on radar. There are two very different structures they can take. One produces most of the long-track history-making tornadoes. The other produces quieter destruction that often catches people unaware. Both are going to show up tonight. There are two main types of severe thunderstorm, and they behave almost like different species of animal. The first is the supercell. It is a single, isolated, rotating thunderstorm that can last for hours. It stands alone on the radar, sharp-edged and menacing. Its updraft is strong enough to suspend giant hail. Its rotation is organized enough to spawn long-track, violent tornadoes. When forecasters use the word supercell, they are describing the most dangerous kind of storm the atmosphere produces on Earth. The second is the squall line, also known as a bowing segment. It is a long chain of thunderstorms stretched out like a wall, sometimes hundreds of miles long, moving together as a single front. Inside that wall, winds can accelerate into damaging straight-line bursts. Brief spin-up tornadoes can drop and lift along its leading edge. The damage path is wide, but usually less intense than a major supercell. Tonight's forecast expects both. The early phase, when storms first fire along the dry line and warm front, favours supercells. Those are the discrete storms the Storm Prediction Center has specifically flagged for tornado potential. Each of them stands alone, pulls in its own fuel, and rotates independently. If any one of them turns in the right direction with the right shear profile, it can drop a significant tornado. As the afternoon fades, the supercells tend to merge. That merge is the transition. When individual storms collide and organize into a chain, they form a squall line. The line itself loses some of the rotation that produced tornadoes earlier, but it gains in another dangerous way. A bowing squall line packs its outflow into a concentrated wall of wind. That outflow can race east at 60, 70, sometimes 80 miles per hour, flattening trees and downing power lines across a path hundreds of miles wide. Squall lines are the reason thousands of people lose power on severe weather nights. The Storm Prediction Center's outlook for the coming days has specifically described storms that will develop as discrete supercells initially, then grow upscale into bowing segments overnight, moving east-southeast into a strong low-level jet. That language tells forecasters exactly what to prepare for. First, the tornadoes. Later, the wind. Both phases matter, and the 2026 season has so far been producing an unusually active mix of both. The April 17th outbreak began with discrete supercells and ended with a sprawling squall line that delivered damage across multiple states. The 46 tornadoes from that event did not all come from the same storm type. Some were supercell tornadoes with long tracks. Others were brief spin-ups from bowing segments late at night. That distinction matters more than it sounds. Supercell tornadoes are typically easier to warn. They develop gradually, and radar operators can track their rotation for 10 to 30 minutes before a touchdown. Squall line tornadoes are harder. They form fast, often in less than a minute, embedded inside a wall of rain that makes them invisible to the eye. They're also more common at night, when squall lines tend to thrive and supercells tend to weaken. Most of the country's dangerous nighttime tornadoes are squall line tornadoes, and this is where the second type of severe storm begins to take over once the sun goes down. After the discrete supercells weaken in the evening hours, the squall line that forms in their wake can continue producing tornadoes for hours after dark. The radar signatures are subtle, the warning windows are shorter, the public is asleep. The technical name for that kind of nighttime tornado has one of the least memorable acronyms in meteorology, but understanding it may be the single most useful thing any person living in this corridor could learn. The deadliest tornado of any given night is often the one no one sees coming. It has a technical name that almost nobody uses in conversation. Forecasters call it a QLCS tornado. The letters stand for quasi-linear convective system, which is just a formal way of saying a long line of storms. A QLCS tornado is a tornado that spins up inside one of those lines, usually along the leading edge where the wind is bending and bowing forward. These tornadoes form fast and die fast, and they kill. Here is what makes them so dangerous. A supercell tornado typically develops from a mesocyclone, the rotating core of the parent storm. That mesocyclone can be tracked on radar for 20 or 30 minutes before a tornado drops. By the time the funnel touches the ground, emergency managers usually have been watching it develop for most of a local news broadcast. Warnings go out early, sirens sound in advance, people have time to move. A QLCS tornado has none of that runway. It forms inside the leading edge of a squall line, where a bulge in the wind structure creates brief, tight rotation. The spin goes from non-existent to ground-touching in under 5 minutes, sometimes in under 2. Radar algorithms that were designed to detect rotating mesocyclones often miss it entirely, because the rotation never spends long enough at any one altitude to trigger the usual signatures. Warning lead times for QLCS tornadoes are often counted in seconds, not minutes. And the timing is the other part of the problem. Squall lines tend to peak in the overnight hours. That is because the low-level jet, the ribbon of fast wind close to the ground, strengthens after sunset. It feeds the squall line into the night. That is exactly the phrase in tonight's outlook. Storms expected to grow upscale into bowing segments overnight, moving east-southeast into a strong low-level jet, into a strong low-level jet, into a sleeping population. Research on tornado fatalities has shown for decades that the nighttime tornado is disproportionately deadly. Some studies have put the fatality rate at roughly twice that of daytime tornadoes of comparable intensity. The reasons are not mysterious. People are asleep, phones are silent. Sirens outside a closed bedroom window do not wake a person the way a conversation does. And mobile homes, which make up a significant share of housing in the rural South and Midwest, offer almost no structural protection against tornado-strength winds. QLCS tornadoes exploit all three of those vulnerabilities at once. This is one of the reasons forecasters have pushed hard in recent years for something called wireless emergency alerts, the federal system that pushes tornado warnings directly to every cell phone in a warning polygon. Even that system has its limits. Phones on silent may not audibly alert. Phones outside cell coverage will never get the message. And in the specific case of a QLCS tornado, even a perfectly functioning system may only give its recipients 3 or 4 minutes. 3 or 4 minutes is enough if you are awake and sheltered. It may not be enough if you are asleep in a manufactured home on the edge of a small town. The 2026 season has already produced QLCS tornadoes across the Midwest. Some were brief and caused minor damage. Others carved meaningful paths through rural areas. The April 17th outbreak included both daytime supercell tornadoes and a nighttime squall line that continue producing severe weather well after midnight in some regions. Tonight's storm will almost certainly produce more of them, and alongside the tornado risk, the storms will produce one more kind of destruction that has quietly been the biggest driver of insurance losses across the country in recent years. It does not sound dramatic. It does not spin, but it falls from the sky in stones that have grown, in 2026, to sizes that used to be treated as impossible. Earlier this year, a hailstorm in Illinois dropped stones measured at more than 6 inches in diameter. That is a state record. It is also a physical achievement that, until recently, meteorologists would have described as rare. 6-inch hail is softball-sized. A hailstone that wide falling at terminal velocity can reach speeds close to 100 miles per hour by the time it strikes the ground. It has enough energy to punch through a vehicle roof, enough to destroy a solar panel in one impact, enough to fracture the skull of any animal caught in the open, including a person. The physics of how the atmosphere grows a stone that large is worth understanding. A hailstone begins as a small ice crystal high inside a thunderstorm, usually at altitudes where the air is already below freezing. As the storm's updraft lifts the crystal, it passes through zones where supercooled water droplets are floating. Those droplets freeze on contact, layering more ice onto the stone. Each round trip through the updraft grows the stone bigger. Each trip adds another layer of ice. If you slice a large hailstone open, you can often see those layers like rings in a tree. The key variable is the strength of the updraft. A weak updraft can only support small hailstones before they fall out of the bottom of the storm. A strong updraft can hold them in the growth zone for minutes at a time, cycling them through over and over until the stones grow too heavy for even a powerful storm to keep airborne. To produce 6-inch hail, the updraft has to be capable of supporting a softball. That takes an immense column of rising air, fed by the kind of high Cape values forecasters have been tracking this spring. 2,000 to 3,000 joules per kilogram can produce large hail. Values above 4,000, combined with the right wind shear and temperature profile, can produce the monster stones that make state records. The 2026 hail season has been running hot for reasons that connect back to everything discussed in earlier chapters. The dry line has been active. The warm Gulf moisture has been reaching far north. The low-level jet has been delivering fuel into storms after dark, and the wind shear aloft has been sufficient to organize strong, long-lived updrafts. Each of those ingredients individually produces a normal severe weather day. Stacked together, they produce events that break records. The Catality 2026 Severe Convective Storm Report identified more than 43 million properties across the United States at moderate or greater risk of hail damage. That number alone should land with some weight. 43 million properties, not buildings in the path of a single storm, properties carrying ongoing annual risk. That figure is roughly equivalent to 1 in 3 housing units in the country. The financial exposure behind that number is staggering. The same report placed the total reconstruction cost value at risk at about $17.8 trillion. That is the replacement cost of everything that could be damaged if hail continued hitting the wrong places at the wrong time. It is larger than the annual output of most national economies on Earth, and the single metro area with the largest slice of that exposure is not where most people would guess. It sits nowhere near Tornado Alley. It is not a southern plains city. It is a place known for lakes, steel, and wind off a very large freshwater coast. And the reason it carries more financial hail exposure than any other metro in the United States is a story about real estate, not meteorology. It is a story that is going to surprise most people. The scale of American exposure to severe storms has quietly doubled under the surface, and most people have never seen the number. The 2026 report from Catality, a major property and insurance analytics firm, identified over 43.5 million properties across the United States with moderate or greater risk of damage from severe convective storms. Those are the storms discussed in every previous chapter. Tornadoes, damaging winds, large hail, all of it grouped under a single technical label. 43 million properties is roughly the population of Spain. And behind those properties sits a reconstruction cost value of $17.8 trillion. That is an industry measurement of what it would cost to rebuild every affected structure at current material and labor prices. It is different from market value. It is different from assessed value. It is the raw engineering price tag of replacement. The meaning of that number is not primarily about insurance. It is about the fact that the country has built itself into the path of storms that used to hit emptier land. For most of the 20th century, severe weather corridors in the United States ran through sparsely populated farmland. A tornado in Oklahoma might never touch a building. A hailstorm in Nebraska might destroy a cornfield, but not a single house. The population of the Great Plains was small. The cost of damage was contained by geography. That geography has changed. Suburbs have spread into former farmland. Metro areas have pushed outward into regions that were once rural. Interstate highways have pulled population centers together, and in some parts of the country, entire new neighborhoods have been built on ground that sits squarely inside the severe weather corridor. Each of those new structures adds to the exposure number. The Catality analysis identifies Texas as the state with the highest overall exposure. That is not surprising. Texas has the largest population of any severe weather-prone state. It has enormous metro areas in Dallas-Fort Worth, Houston, and San Antonio, all of which sit inside corridors that regularly see tornado and hail events. A single large hailstorm across the Dallas-Fort Worth metroplex can generate billions of dollars in insured losses in a matter of hours. That has happened multiple times in recent years, but the more surprising entry in the report is the one sitting next in the rankings. It is a metro area that most Americans do not think of as severe weather country at all. The Catality analysts even gave the pattern a name. They called it the Chicago anomaly. The name fits. The Chicago metro area, stretching from northwestern Indiana across the top of Illinois, holds more financial exposure to severe convective storms than any other metro area in the country. Its reconstruction cost value at risk reaches approximately $1 trillion. That is not a typo. $1 trillion in replacement cost, concentrated in a single region that most people associate with lake effect snow and deep dish pizza. The mechanism behind the Chicago figure is not primarily weather, it is density. Chicago is one of the most densely built metro areas in the country, with tightly packed high-value real estate, towering commercial infrastructure, and millions of homes compressed into a relatively small footprint. When a hailstorm or a derecho sweeps across such a region, it damages an enormous number of properties at once. This storm does not need to be unusually strong, it just needs to hit that footprint. And Chicago, as the past few years of data have shown, is a target the atmosphere keeps finding. Illinois currently leads the country in tornado, hail, and wind reports for 2026. The state's exposure is not hypothetical. It is being tested in real time. The towns already hit this year were smaller places with lower exposure. The question hovering over the rest of the season is whether a large-scale event finally reaches the metro itself. Because the reason one city carries that much risk is not just that it is big. It is that America's severe weather corridor has been quietly moving in its direction for 2 decades. And the geography behind that shift is something the old maps no longer show. The Chicago anomaly is what happens when 2 trends meet in the same place at the same time. The first trend is density. The Chicago metro has been building upward and outward for more than a century. Dense high-rise commercial cores, vast suburban rings, industrial corridors along the lake, manufacturing districts on the south side, residential neighborhoods in the north. Each of those structures represents a dollar amount that has to be replaced if severe weather strikes. When you add those dollar amounts together across the roughly 9.5 million people who live in the metro, you get the $1 trillion exposure figure. That is the financial side of the anomaly. The second trend is atmospheric. For roughly 2 decades, researchers have been tracking a slow eastward shift in the heart of the American severe weather corridor. The traditional tornado alley centered on Oklahoma and Kansas has seen declining tornado frequencies in recent years relative to the long-term average. Meanwhile, states further east, including Mississippi, Alabama, Tennessee, Illinois, and Indiana, have seen rising numbers. The center of gravity is moving. Scientists have called this informally the tornado alley shift. The research on it is still evolving. Different studies have proposed different causes, including changes in jet stream behavior, increased Gulf moisture penetrating further east, and long-term shifts in land surface temperature patterns. Not all of the proposed causes have equal evidence. What they share is the observation itself. The map is drifting east. Illinois now sits closer to the center of the new map than the old one, and Chicago, the largest metro in Illinois, is the single largest population concentration inside the drifting zone. The city itself has historically seen relatively few tornadoes within its urban core. The surrounding counties have seen more. The 2026 season has tested this specifically. The April 17th outbreak, which produced 48 tornadoes across multiple states, sparked 2 house fires in the Chicago area. Those were not direct tornado hits on the city itself. They were indirect consequences of the larger storm system passing through the region. But the close call is the pattern to watch. When a metro area the size of Chicago, carrying the financial exposure it does, sits inside an atmospheric corridor that is growing more active year by year, the probability equation starts to look uncomfortable. It is not that a single disastrous event is guaranteed. It is that the odds of one keep climbing, and the insurance industry has been adjusting its models to match. Insurance companies do not make these adjustments on instinct. They make them on data. Catality and similar analytics firms have been running catastrophe models for decades, simulating thousands of possible storm seasons to estimate the distribution of possible losses. For most of the 20th century, those models treated Chicago as a moderate risk zone for severe convective storms. In the last several years, that ranking has climbed. The 2026 report placing Chicago at the top of the financial exposure list is the latest step in a trend that has been building. What it means for the residents of the metro is not that a tornado is imminent tonight. It means that the underlying risk has shifted. The premiums reflect it. The building codes are beginning to reflect it. The emergency management plans reflect it. And the next major outbreak that aims its corridor further east than usual will find a much bigger population of structures waiting for it than the old map would have predicted. That is the deeper meaning of the Chicago anomaly. It is not really about Chicago. It is about the quiet, steady eastward migration of America's severe weather risk into the places where Americans actually live. The cities, the suburbs, the metro areas built during decades when the storm maps looked different. The risk did not stand still. The country did not stand still. And the two are now colliding in ways that the old forecasts were never designed to handle. The Chicago story is one example. It is not the only one. Because the country's second great severe weather corridor has a problem of its own. It lives further south. It operates mostly in the dark, and it kills people at rates that the plains corridor almost never matches. The geography of American severe weather has been moving east for decades, and the data behind that shift is now solid enough that insurance companies have rebuilt their models around it. Tornado Alley as a term was coined in the mid-20th century to describe a corridor running from North Texas up through Oklahoma, Kansas, and Nebraska. That corridor was where most of the country's tornadoes happened, where the highest intensity events clustered, and where storm chasers built their careers. For most of the 20th century, the label fit the map. Then the map started drifting. Peer-reviewed research tracking tornado reports over the past several decades has documented a steady decline in tornado frequency across parts of the traditional alley: Oklahoma, Kansas, western Texas. At the same time, frequencies have climbed across states further east: Mississippi, Alabama, Tennessee, Kentucky, parts of the Midwest, including Illinois and Indiana. The tornadoes did not disappear, they relocated. Scientists are still working out why. Several mechanisms have been proposed, and the honest answer is that no single one has been confirmed as the dominant cause. Some research has pointed to long-term shifts in jet stream patterns, with the ridge and trough structure that drives severe weather setting up further west than it used to. Other research has focused on warmer Gulf of Mexico surface waters, which allow moist, unstable air to penetrate further north and east than in previous decades. Other studies have looked at changes in the temperature contrast between the Great Plains and the southeastern United States. Probably all of these factors contribute to some degree. None of them fully explains the shift alone. What is not debated is the observation. Tornado databases maintained by the National Weather Service show it clearly. The center of American tornado activity has been sliding east at a measurable rate for roughly the last 20 years. Communities that rarely saw tornadoes a generation ago now sit inside corridors that see them regularly. The consequences of that shift are not evenly distributed. Eastern severe weather corridors differ from the traditional plains in several important ways. The plains are flat, open, and sparsely populated outside of their major metros. A tornado crossing rural Kansas may never encounter a structure. The southeast and the Midwest are hillier, more forested, and significantly more densely populated. Tornadoes in those regions are more likely to strike towns, more likely to hit forests, where the storms become harder to see, more likely to arrive at night, and the population density means more people are in the path when they do. The 2026 season so far is consistent with the long-term pattern. Illinois leads the country in tornado reports. Mississippi ranks second. The traditional leaders from the Old Alley rankings are further down the list. The eastward drift is not some abstract future possibility. It is what is happening right now inside the same season tonight's storm is part of. This matters for viewers living in the eastward corridor for a specific reason. Building codes in many eastern states were written before the shift became apparent. Public awareness of tornado risk is often lower than in the plains, where generations of residents grew up with tornado drills. Basement construction is less common in the southeast than in the northern plains, and the kind of terrain that hides tornadoes from sight, forests and hills, makes visual detection slower. All of those factors combine to raise fatality rates per tornado in the eastern corridor. The next step of the story lies further south, because there is a specific zone where those eastward corridors thicken, and where the combination of nighttime storms, forested terrain, and vulnerable housing has produced one of the deadliest severe weather regions in the world. There is a region in the southeastern United States that severe weather researchers call Dixie Alley, and tornadoes that strike it are disproportionately deadly. The zone runs roughly from eastern Arkansas and Louisiana across Mississippi, Alabama, and parts of Tennessee and Georgia. Unlike the traditional Plains Alley, Dixie Alley does not see the largest number of tornadoes. It sees something more dangerous. It sees a combination of factors that make each tornado, on average, more likely to kill. The reasons behind that lethality are stacked on top of each other. The first is timing. A significant share of tornadoes in Dixie Alley occur at night. The secondary tornado season in the region, centered on the fall months, is especially prone to nighttime activity. Even in the spring, the geography means storms often fire in the late afternoon over the Mississippi River Valley and reach Alabama and Georgia after dark. A nighttime tornado is, by most studies, roughly twice as deadly as a daytime tornado of comparable strength. People are asleep. People are slower to respond. The funnel is invisible. The second factor is terrain. Dixie Alley is heavily forested in many places. Rolling hills and dense tree cover obscure tornadoes from view until they're dangerously close. In the open plains, a tornado on the horizon can be visible from miles away, giving residents time to react. In the wooded hills of Alabama, a tornado may not be seen at all until it is over your street. That visibility gap is measured in the fatality statistics. The third factor is housing. Dixie Alley has one of the highest concentrations of manufactured homes in the country. Those structures, sometimes called mobile homes, offer almost no protection against tornado-strength winds. Even a relatively weak tornado can destroy a mobile home completely. Stronger tornadoes will roll them, shred them, or throw them hundreds of yards. In a region where mobile home residency is common, the housing itself becomes a fatality multiplier. The fourth factor is precipitation. Storms in the southeast often produce what meteorologists call high precipitation supercells. These are rotating thunderstorms that generate so much rain that the tornado at their core is wrapped inside a wall of water. Forecasters call them rain-wrapped tornadoes, and they are some of the most dangerous storms in existence. You cannot see them. You cannot hear them over the rain. By the time the funnel is close enough to be obvious, it is too late to move. All four of these factors stacking on the same map explain why fatality rates in Dixie Alley run consistently higher than the national average for comparable tornado strengths. The 2026 season has been quieter than some in the southeast, with the main action so far concentrated further north. But the potential for a major Dixie Alley event remains through the spring, especially as the jet stream pattern continues to feed moisture north out of the Gulf. Forecasters are watching it. The residents of the corridor are watching it, because many of them have lived through major outbreaks before. The long-term picture is the one to focus on. Research on nighttime tornadoes has been consistent for years. People living in Dixie Alley, and in any region where nighttime tornadoes are common, are the ones most in need of redundant warning systems. A single siren network is not enough. A single cell phone alert is not enough if the phone is silent or outside coverage. Weather radios that activate automatically on warnings combined with neighborhood-level awareness have been shown to save lives in this corridor. That advice is simple, boring, and repeatedly ignored. Because in the end, the most important factor in whether a tornado kills is not how strong the tornado is. It is what the person in its path is living inside when it arrives. And the single structure type most likely to produce fatalities in an American tornado is one that sits, today, on millions of lots across the country. A mobile home in the path of a tornado is the single strongest predictor of whether the event becomes a mass casualty incident. That sentence is not dramatic, it is statistical. Research on tornado fatalities going back decades has consistently shown that residents of manufactured homes account for a disproportionate share of tornado deaths in the United States. The exact percentage varies by study, but the pattern is stable across all of them. A person in a mobile home during a tornado is many times more likely to die than a person in a site-built house a few blocks away. The mechanism behind that statistic is structural. A mobile home is typically built on a steel chassis and anchored to the ground using metal tie-downs that connect to concrete anchors. Even when installed correctly, those tie-downs are designed to resist the kind of straight winds that occur in most thunderstorms. They are not designed to withstand the rotational pressures of a tornado. A tornado does not push a home from one direction. It applies differential pressures to every surface simultaneously, combined with uplift forces from below. Under those forces, mobile homes do not shelter. They fail. A weak tornado, an EF0 or EF1, can roll a mobile home off its foundation. A moderate tornado, an EF2, can destroy one completely. A strong tornado, an EF3 or above, can reduce a mobile home to debris scattered across multiple counties. The occupants inside, no matter how well prepared they were, have almost no chance of surviving in place if the home takes a direct hit. The only safe option is to leave before the storm arrives. Every tornado safety briefing produced by the National Weather Service in recent years has emphasized this point. If you live in a mobile home and a tornado warning is issued, do not shelter in place. Leave. Go to a neighbor's basement. Go to a community storm shelter. Go to any nearby site-built structure. Do not stay. That advice is easy to read and hard to follow. Many mobile home residents are people with limited transportation, limited shelter options, and limited time to evaluate risk. Many live in rural areas where the nearest site-built structure is miles away. Many receive tornado warnings while they're asleep, too late to drive anywhere safely. The warning is clear. The execution is difficult. That gap between advice and reality is where the fatalities happen. Some states and counties have invested in community storm shelters specifically for manufactured home residents. Parks have been built with underground concrete shelters sized for the full community. Emergency managers have distributed weather radios at reduced cost to families in high-risk housing. These efforts have demonstrably saved lives. They are also not universally available. In a country with millions of manufactured homes, many of them in rural areas far from purpose-built shelter infrastructure, the shelter gap remains enormous. When a tornado hits a mobile home park at night, the casualty count is almost always higher than the same tornado hitting a subdivision of site-built houses. This pattern is one of the most replicated findings in severe weather research. For tonight's storm, and every storm like it, the population most at risk is not spread evenly across the warning polygon. It is concentrated in specific housing types, on specific lots, in specific regions where the intersection of housing and weather geography has been painful for decades. The atmosphere does not target them. The statistics do. And even for people living in sturdy site-built homes, the warning system itself has limits that the public rarely sees until it fails. One of those limits failed earlier this year, in Michigan, with consequences that are now part of an active investigation. The average lead time for a tornado warning in the United States is about 13 minutes. When the system works, that is enough. When the system fails, 13 minutes can become 0. Earlier this year in Michigan, the system failed. A small tornado outbreak struck a 3-county area of the state during a period when the Storm Prediction Center had rated the area at only marginal risk, the lowest level on the 5-level scale. Because the outbreak was concentrated in such a small geographic zone, radar and forecasting tools had difficulty detecting the rotation early enough to issue a tornado watch in advance. No tornado watch was put into effect for the area during the outbreak. No watch, no early alert, and people died. The Michigan governor's office subsequently called for a probe into why no tornado watch had been issued. Questions were raised publicly about whether staffing or funding cutbacks at the National Weather Service had played a role. Those questions remain the subject of ongoing investigation. The broader issue is the warning architecture itself. The National Weather Service issues warnings based on a combination of radar data, ground reports, and automated detection algorithms. The system works extremely well most of the time. It has improved dramatically since the 1970s, when many major tornadoes struck with little to no warning. Today, the average lead time is better than it has ever been, but averages hide variation. For some storms, particularly weak, short-lived tornadoes that form quickly inside squall lines, lead times can be very short, sometimes 0. The radar takes time to scan the atmosphere. An algorithm takes time to process rotation. A human forecaster takes time to decide whether to issue a warning. Communication takes time to reach the public. All of those time delays are measured in seconds. They add up. For some regions, particularly rural areas far from the nearest radar site, the warning lead time is systematically shorter because the radar cannot see as well at long ranges. Radar beams rise with distance from the antenna. At very long distances, the beam may pass over the top of a tornado entirely, missing the rotation at ground level. There are known radar gaps in the United States. The eastern plateau of Tennessee, parts of the Ozarks, sections of the northern Rockies, rural Alabama. In these zones, the lowest radar coverage is poor, and tornadoes that form close to the ground may be invisible to the primary detection network. Backup systems exist, including storm spotters and mobile radar. They help, They do not fully fill the gaps. The warning system is only as good as the weakest link in a long chain. That chain includes the forecasters, the radar network, the communication infrastructure, the public alert systems, and the individuals who receive the alerts and decide what to do. A break at any link weakens the whole. And in 2026, with a severe weather season running hotter than forecast, every link is being tested. The 2026 season has already produced questions about whether the system is meeting the demands being placed on it. The Michigan case is one example. Other regions have raised similar concerns about whether the warning network can keep up with the pace of outbreaks. Forecasters themselves have spoken publicly about the stress on their offices. 128 warnings in a single office through April alone, as the Chicago office reported, is an enormous workload, which makes the political fight happening in the background of all of this more consequential than it might appear, because the funding of the system that produced those warnings is now itself a matter of dispute. In the background of the 2026 severe weather season, an argument about federal weather funding has been playing out in real time, and it collided directly with one of the year's deadly outbreaks. After the Michigan outbreak earlier this year produced fatalities without a tornado watch in effect, the state's governor publicly questioned whether proposed budget cutbacks to the National Weather Service might have contributed to the forecast gap. The Michigan case has become a reference point in ongoing debates about Federal Weather Service staffing and funding levels. The politics are heated. The operational questions are real. The National Weather Service operates 122 local forecast offices across the country. Each office is staffed by a team of meteorologists who handle 24-hour forecast coverage, including the critical job of monitoring radar and issuing severe weather warnings during active events. These offices are the backbone of the public warning system. Every tornado warning that reaches a cell phone originates in one of them. Staffing those offices is not simple. Experienced severe weather forecasters take years to train. They require specialized education, extensive on-the-job experience, and ongoing certification. When an office is short-staffed during a major outbreak, the consequences are not just inconvenient. They can be measurable in warning lead times, in detection accuracy, and in the quality of communication between the forecast office and local emergency managers. The 2026 season has stressed the system. Forecast offices across the central United States have been handling near-continuous severe weather for weeks. Chicago's record warning count, Illinois leading the country in tornado, hail and wind reports, multi-state outbreaks requiring coordination across offices. The operational load on the system has been heavy, and the season is not over. That context is where the funding debate lands. The argument is not whether weather services matter. Almost no one disputes that. The argument is whether the current level of investment is adequate for a country whose severe weather exposure has grown substantially in recent decades. The Catality 43 million property figure is one measure of how much exposure has grown. The frequency of outbreaks striking populated regions is another. Forecasting technology has improved dramatically. The question is whether the human and infrastructure investment has kept pace. Scientists working in severe weather research have spoken publicly in recent years about their concerns. Radar networks need continued modernization. Satellite capabilities need continued funding. Forecast offices need staffing that can handle the surge demands of active seasons like this one. Proposals to reduce budgets in any of those areas have drawn pushback from within the meteorological community. The argument is ongoing and not close to resolution. What is worth understanding for any viewer inside tonight's warning polygon is that the forecast you are hearing on your local news was produced by a specific office with specific staffing. The warning you may or may not receive later tonight will depend on the operational capacity of that office in the moment the storm arrives. Most of the time, the system works. It works because people who have trained their entire careers are at their desks when the storms fire. But the margin between a warning issued in time and a warning issued too late is narrow. It is measured in minutes, in some cases in seconds, and any pressure on the system that reduces the number of skilled hands watching the radar during an active event reduces the country's collective safety net. The 2026 season is demonstrating that this margin matters, which leads to the question of where the system can still see clearly and where it cannot. Because not all parts of the country have equal access to the radar network, and the holes in that network have specific geographies that every forecaster knows by heart, specific locations that meteorologists have been trying to close for decades. The primary network is called NEXRAD. It consists of roughly 160 high-powered Doppler radar sites distributed across the United States. Each radar can scan out to about 230 miles for precipitation, and somewhat further for weaker returns. When you combine the coverage of all sites, most of the country sits within range of at least one radar. But range is not the same as useful coverage. A radar beam does not travel in a straight line close to the ground. As the beam travels outward from the antenna, the curvature of the Earth causes it to climb. At 50 miles out, the lowest beam angle is already several thousand feet above the ground. At 100 miles out, it can be more than a mile up. At the edge of the range, the radar may be scanning through the middle of the atmosphere, well above where a tornado forms. That geometry creates low-level coverage gaps. In those gaps, the radar may detect that a storm exists and may see its upper levels clearly. But the rotation near the ground, which is what produces a tornado, may be invisible to the scan. Forecasters rely on algorithms that extrapolate from upper-level signatures, on ground-based spotter networks, and on experience to fill those gaps. It is not a perfect system. The known low-coverage zones in the United States include parts of the northern Rockies, sections of the Ozarks, much of western Texas away from the Dallas-Fort Worth and Midland radar sites, and stretches of the Mississippi River Valley where the nearest radar is too far from the storm environment. Some of those gaps overlap with areas of high severe weather risk. The consequences show up in warning data. Studies examining tornado warning lead times by region have shown that gaps in radar coverage correlate with shorter average lead times and with higher false alarm and miss rates. This is not a secret or a scandal. It is a well-documented limitation of the network, and the National Weather Service has been pushing for targeted gap-filling radar installations for years. Progress has been slow because radars are expensive. A single NEXRAD installation, including the tower, the shelter, the radar itself, and the communications infrastructure, can cost tens of millions of dollars. Adding more sites to close gaps is not a decision that gets made in a single budget cycle. It requires long-term planning, which requires long-term funding. In the meantime, the gaps exist. For any given severe weather event, the quality of the warning depends partly on where the storm happens to form. A supercell that develops directly above a radar site has its rotation tracked in detail. A supercell that develops at the edge of two radar coverage areas, each of them distant, is harder to track. The rotation may still be detected, but it may be detected later, or with less confidence. Tonight's storm corridor is mostly well covered. The Central Plains and the Midwest have relatively dense radar coverage, with overlapping sites. The warnings issued tonight will benefit from that overlap, but this detail is worth remembering for the broader picture. Not every part of the country has the same warning quality. not every storm is scanned equally. And as the severe weather corridor shifts, as discussed in earlier chapters, the question of where the radar network is and is not adequate becomes more urgent. All of these layers, from the housing problem to the warning system to the radar gaps, stack on top of each other to explain why severe convective storms have become one of the most expensive hazards in American insurance history. The number is staggering, and the industry is still adjusting. Severe convective storms, the category that includes tornadoes, damaging winds and hail, now generate losses that rival major hurricanes for the American insurance industry. That is a shift the industry has been tracking for years. A single extreme hailstorm can, in modern dollars, generate insured losses comparable to a Category 4 hurricane landfall. That sentence would have sounded wrong 30 years ago. Hurricanes were the benchmark catastrophe. Everything else was secondary. That benchmark has shifted. The 2026 Catality Report makes the case explicitly. Severe convective storms, the report observes, have evolved from secondary concerns to primary drivers of annual insured property losses in the United States. The reasons are stacked. More exposure because more property now sits in severe weather corridors. More severity because the largest hail and the most damaging winds appear to be producing more damage per event. More frequency because outbreaks have been running at or above historical averages for several seasons. Each of those factors independently raises insurance costs. Stacked, they transform the industry. The financial response has been dramatic. Insurance premiums in severe storm-exposed states have climbed substantially in recent years. In some markets, insurers have withdrawn from certain types of coverage entirely. Reinsurance companies, which provide insurance to insurance companies, have revised their models to reflect higher expected losses from severe convective storms in the central and southeastern United States. These are not small adjustments, they are structural changes. For homeowners, the consequences show up in premium notices. A family living in central Texas or northern Alabama may see annual premium increases of 20, 30 or 40% in a single renewal cycle, depending on where they sit in the risk maps. For commercial property owners, the increases can be even larger. For developers considering where to build new housing, the insurance landscape is now a meaningful input into site selection. All of this is driven by the underlying physics. The storms themselves are not dramatically more common than they were decades ago, although there has been some increase. What has changed more than the storm frequency is the exposure underneath the storms. The country has built itself into the path, suburbs have expanded, metro areas have grown, commercial districts have sprawled outward. When a storm hits the same region it would have hit in the 1970s, it now hits more stuff. More stuff equals more dollars equals higher insured losses. That does not mean storm intensity has been static. Some research has suggested that the largest hail events have grown more common in recent decades, and that damaging straight-line wind events have also trended upward in certain regions. Climate scientists have debated how much of that trend is driven by long-term warming and how much by decadal natural variability. The honest answer is that the research is still being worked out. What is not debated is the insurance picture. Major insurers now treat severe convective storms with the same strategic seriousness they once reserved only for hurricanes. Internal models have been rebuilt. Premium structures have been adjusted. Reinsurance treaties have been rewritten. The industry has accepted that the old category ranking no longer holds. Tornadoes, winds, and hail have become co-equal partners with hurricanes in the American catastrophe list. For a viewer sitting inside tonight's Polygon, this shift has a personal meaning. Your insurance policy, whatever it covers, has been shaped by models that assume storms like the one coming tonight are going to keep happening. The premium you pay reflects those assumptions, the coverage terms reflect those assumptions, and the reason the industry has made those assumptions is the same reason the fatality number is so large. The country has more to lose than it used to, $17.8 trillion worth, concentrated in the zones the atmosphere keeps hitting. This $17.8 trillion figure from the 2026 fatality report is one of the most concrete measurements of American exposure to severe weather ever produced. To put that number in context, it is larger than the annual output of most major national economies. It is roughly 2/3 of the entire United States gross domestic product. It represents the current replacement cost of the built environment sitting inside moderate or greater severe convective storm risk zones across the country. That includes homes, commercial buildings, schools, hospitals, roads, and infrastructure. Every dollar of that total is a dollar that could, in principle, be damaged or destroyed. In any given year, only a small percentage of that exposure is actually affected by severe weather. The atmosphere does not hit everything simultaneously. Even in the worst seasons, most of the $17 trillion remains untouched. What matters is the trajectory. The number has been climbing year after year as the country continues to build in exposed regions. That climb is not slowing. Population growth in severe weather-exposed states has continued, in some cases accelerating. Texas, Florida, Georgia, Tennessee, and the Carolinas have all seen significant population gains in recent years. Each new housing unit built in a risk zone adds to the exposure total. Each new commercial development adds more. Insurance companies see the trend line. Their actuarial models reflect it. Their premium structures reflect it. Their willingness to offer coverage in certain markets reflects it. For homeowners, the practical consequence is the rising cost of protection. For the broader economy, the consequence is a growing share of national wealth concentrated in places where severe weather can reach it. Historically, coastal exposure was the dominant concern because of hurricanes. Today, inland exposure is rising to match it. A country that once thought of hurricane risk as the primary severe weather challenge now has to think equally about severe convective storm risk across huge sections of the interior. Policymakers have begun to respond, though unevenly. Some states have updated building codes to require stronger roofing, better wind resistance, and more hail-resistant materials in high-risk zones. Some communities have invested in storm shelters for neighborhoods lacking basements. Some insurance programs now offer discounts for hail-resistant roofing or impact-rated windows. These measures help at the margins. At the national level, the response has been fragmented. There is no single federal program that addresses severe convective storm risk, the way the National Flood Insurance Program addresses flood risk. There is no unified mitigation strategy. Research funding for severe weather has grown in recent years, but remains modest compared to the scale of the exposure. The gap between the $17 trillion exposure and the resources allocated to reduce it is enormous. For tonight's viewers, the practical implication is not abstract. The country is more exposed than it used to be. The insurance system has adapted in ways that affect household budgets. The warning system has improved but still has gaps, and the atmosphere shows no sign of giving the country a quiet season to catch up. All of which leaves one particularly dangerous hazard that tonight's forecast keeps mentioning, and that most viewers underestimate every time they see it listed. It is not the wind. It is not the hail. It is not even the tornadoes. It is the water. Year after year, the single deadliest element of severe thunderstorms in the United States is not the tornado. It is the flash flood. That fact catches most people off guard. Tornadoes get the news coverage. Tornadoes have the dramatic footage. Tornadoes stay in the public imagination because they are visually unforgettable. But the statistics from the National Weather Service consistently show that flash flooding produces more fatalities on average than any other single thunderstorm hazard. And forecasters in 2026 have been repeating this warning for weeks. AccuWeather meteorologists, among others, have specifically flagged flash flooding as one of the biggest concerns of the current severe weather season. Heavy downpours, combined with already saturated ground in many regions, produce the conditions where small streams become rivers within minutes, roads become canals, underpasses become death traps. Most flash flood deaths happen in vehicles. The reason is simple physics. Just 6 inches of moving water can knock an adult off their feet. Just 2 feet of moving water can float most cars, trucks, and even sport utility vehicles. Drivers routinely misjudge flood depths on roads, especially at night, and attempt to cross water that will carry them away. The vehicle goes downstream. The occupants do not get out in time. The advice is universal and universally ignored. Turn around, don't drown. That phrase has been the National Weather Service's primary messaging for flash flood safety for years. It is simple, it is boring, and it is correct. Every year the same fatalities happen in the same kinds of places to drivers who believe they could make it. Tonight's storm system carries flash flood risk as part of its hazard profile. The mechanics are straightforward. Strong thunderstorms, especially those moving slowly or training over the same area, can drop several inches of rain in a single hour. Urban drainage systems are designed for typical rainfall rates, not extreme ones. When the rate exceeds the drainage capacity, water backs up, streets flood, creeks overflow, low water crossings become impassable, and then people drive into them anyway. Urban flash flooding has become a significant concern in 2026 because of the pattern of persistent storm trains. When a jet stream pattern is stuck, storms repeatedly cross the same geography. Each successive storm falls on ground that is already wetter than the last. Runoff accelerates, flood responses come faster, and what might have been a routine thunderstorm in a dry season becomes a dangerous flash flood event after weeks of repeated hits. Several forecast discussions this season have specifically called out flash flooding alongside the tornado risk. The Weather Prediction Center, the federal agency responsible for precipitation forecasting, issues outlooks that rank flash flooding potential on a 4-level scale. During major outbreak events, those outlooks has been running at the upper end of the scale in regions where storm training is likely. Tennessee Valley, Ohio Valley, parts of the lower Mississippi Valley. The pattern keeps returning to the same places. For viewers inside tonight's polygon, the advice is direct. Do not drive into water. Do not walk through flowing water. If you encounter a flooded roadway, turn around. These sound like obvious statements. They are repeated because the fatalities are repeated. And beyond the immediate flash flood risk, the broader pattern points to something the entire country has to grapple with. More water, more intense rainfall events, more saturated ground, more urban flooding, more dangerous nighttime drives across ordinary streets that have become briefly, lethally impassable. The 2026 season has been a reminder that severe weather is not just about funnel clouds and hail. It is about the full menu of what a violent atmosphere can do. And one of the fastest growing pieces of that exposure is a new kind of infrastructure that almost did not exist 20 years ago. One of the fastest growing exposures to severe weather in the United States is an infrastructure category that barely existed 20 years ago. Utility-scale solar power installations have expanded across Texas, the Plains, the Midwest and the Southeast. These are the vast arrays of photovoltaic panels, sometimes covering thousands of acres, that now generate a meaningful share of electricity for several regional grids. Their geography overlaps directly with the country's primary severe convective storm corridor, and solar panels are vulnerable to hail. The standard utility-scale photovoltaic panel is tested to withstand hail up to a certain diameter, typically around 1 inch. That tolerance is sufficient for the majority of severe weather events. It is not sufficient for the large hail events that have become a signature of recent severe weather seasons. A 2-inch hailstone falling at terminal velocity can shatter a panel. A 3-inch stone will destroy it. A 6-inch stone, like the record-setting event in Illinois earlier this year, will ruin anything within its footprint. Major hail events have already produced multi-million-dollar solar farm losses in recent years. The industry has responded with several mitigation strategies. Some newer installations use panels rated for larger hail. Some use tracking systems that can tilt the panels to a steeper angle during severe weather, reducing the impact surface area. Some rely on specialized insurance products designed specifically for solar exposure. These measures help, but they do not eliminate the risk, and the exposure is growing fast. As solar capacity expands across the country, more installations are landing in severe weather corridors. A single major hail event in the wrong place can destroy tens of millions of dollars of infrastructure in minutes. The financial exposure, in aggregate, has become significant enough that the renewable energy industry now considers severe weather risk a primary siting consideration, alongside sunlight availability and grid connection. The same story applies to other modern infrastructure. Wind turbines in the central United States face their own severe weather exposure, although turbines are structurally more robust against hail than solar panels. Data centers, which have been expanding rapidly into regions like North Texas and parts of the Plains, face exposure from hail, damage to cooling equipment, roof damage, and power interruptions from severe storms. Warehouse and distribution facilities, which dot the country's interior, take similar hits. All of these modern-built assets sit inside the Catality exposure number, and the trend is not slowing. The energy transition is pushing more renewable infrastructure into sunny, windy, and often storm-prone regions. The logistics boom is pushing more warehouses into central locations with good highway access, which tend to overlap with the severe weather corridor. Each new installation increases the country's total exposure to events like tonight's storm. The pattern reveals something about the meaning of the phrase severe weather risk. It is not a fixed feature of the map. It is a function of what is built on the map. As the country continues to build, and to build expensive, complex infrastructure across corridors, the atmosphere has not changed its mind about. The total risk profile climbs regardless of whether storm frequency itself changes. That is why the insurance numbers keep growing. That is why the Catality report exists in its current form. And that is why even a below-average severe weather season, by some measures, can still produce enormous losses. Because below average in frequency does not mean below average in damage. The previous year proved that clearly, with numbers that set benchmarks, the current season is already being compared against. The 2025 severe weather season produced 1,544 preliminary tornado reports across the United States. That number became the benchmark against which 2026 has been measured. It was an exceptional year by most standards. Almost 2/3 of those tornadoes occurred between March and May, the peak severe weather months. Multiple major outbreaks struck across the central and southeastern United States. Casualty figures were significant, insured losses were substantial, and forecasters did not expect 2026 to match it. Long-range forecasts issued in early 2026 predicted a total tornado count between 1,050 and 1,250, which would have been below the historical average of 1,225. That forecast reflected a mix of factors. The collapsing La Nina was expected to weaken somewhat. A shift toward El Niño later in the year was anticipated, and the raw pattern analysis suggested a more typical distribution of events. But the season has not followed the forecast so far. The front-loaded pattern, with unusually active March and early April, has put the 2026 count on a trajectory that is running high for this point in the year. Whether it will end up matching 2025 is still unknown. Seasons can fade, the jet stream can shift. The El Niño transition could reduce activity in the coming weeks. But the damage to tornado ratio is a separate question. Even if 2026 produces fewer tornadoes than 2025, it could still produce comparable or greater damage if the specific storms that do occur strike populated areas. This is the point forecasters have been making repeatedly. Storm counts alone are not the measure of a season. What matters is where the storms land. A single violent tornado through a metro area can produce losses larger than 100 tornadoes in open farmland. The 2025 season produced this lesson clearly. Individual outbreaks during 2025 generated billions of dollars in insured losses. The financial footprint was heavier than the tornado count alone would have suggested, because several of the outbreaks struck regions with high population density and high property values. Each of those events stayed in the insurance industry memory, shaping model assumptions that now inform 2026 pricing. The pattern is consistent with a longer trend. Over the past 2 decades, severe weather damage totals in the United States have climbed substantially, even in years where storm counts were unremarkable. The underlying driver is exposure. More property, more people, more infrastructure sitting in the paths. Each year the exposure grows. Each year, even an average storm season has the potential to produce above-average losses. For 2026, the season is still being written. Tonight's storm is part of the story. The outbreaks in the weeks ahead will continue it. The transition toward El Niño in the second half of the year will shape the latter part of the story. By October or November, forecasters will be writing the season's summary. They will compare it to 2025. They will evaluate whether the front-loaded pattern produced the total losses that would make 2026 stand out, or whether a quieter May and June gave the country a reprieve. There is no way to know in the moment. What is known is that the season so far has demonstrated one thing clearly. The atmosphere in 2026 has been capable of producing intense severe weather on a scale comparable to, or in some specific metrics exceeding, the worst of recent years. The forecast predictions that ran lower have been repeatedly tested. The forecast offices handling the warnings have been working at high operational tempo. Whether that tempo continues through the summer, or whether a quieter pattern takes over, will depend on how several competing forces play out over the coming weeks. And one of the biggest of those forces is a climate signal that has been running for decades, and that scientists have tried hard to describe honestly. The honest answer about how climate change is affecting American severe weather is more nuanced than most headlines, and more revealing than most deniers. Here is what the research actually says, as carefully as it can be summarized. Tornadoes are hard to attribute directly to climate change. The tornado record depends on changes in how tornadoes are reported over time, with more observers, better radar, and more spotters today than in previous decades. That reporting bias makes long-term trend analysis difficult. Some studies have shown modest shifts in tornado activity, including the eastward drift discussed earlier. Others have shown changes in the clustering of tornadoes into larger outbreaks. The overall frequency of tornadoes has not changed dramatically in the raw data, but several of the ingredients that feed tornadoes have. Sea surface temperatures across the Gulf of Mexico have warmed measurably. That warming increases the moisture content of the air, flowing north into the severe weather corridor. More moisture means higher dew points. Higher dew points mean more energy available for storms. This connection is well established in research. Atmospheric instability, the raw fuel for severe thunderstorms, appears to have trended upward in some regions. Hail, another component of severe weather, has shown some evidence of trending toward larger stones in certain areas, though the data is complicated by changes in how hail is reported. Damaging straight-line wind events have also shown signs of increase in some analyses. Flash flooding from heavy rainfall, however, shows a clearer signal. Heavy precipitation events have become more common in the United States over the past several decades, and that trend is consistent with climate expectations about warmer air holding more moisture. All of these signals are partial. None of them individually tells the full story. What they share is direction. Most of the ingredients that enable severe weather have moved in directions that, if anything, favour more intense events. That does not mean every storm tonight is a climate storm. It does not mean 2026 is breaking records because of climate alone. It means the background conditions have shifted in ways that make extreme events somewhat more likely and, when they occur, somewhat more intense. Scientists have been careful not to overclaim. Tornado attribution remains an active research question. The statement, "This storm was caused by climate change," is not a statement most reputable climate scientists would make about any individual event. The statement, "Warmer Gulf waters have increased the moisture available to feed severe storms in the central United States," is a statement most climate scientists would agree with. The difference between those two statements matters. Headlines often collapse the distinction, which has eroded public trust in the underlying science. The careful scientists have been emphasizing a more measured position. Climate change is affecting the environment in which severe weather forms. It is not the single cause of any given outbreak. It is one of many factors, and its influence varies across different types of severe weather. For tonight's storm, the influence of climate change is partial and indirect. For the season as a whole, the influence is probably larger but still difficult to quantify precisely. For the long-term trajectory of American severe weather exposure, the influence is likely to grow. That trajectory matters because it intersects with the exposure numbers discussed earlier. A country that is building more property in severe weather corridors, while the atmosphere is gradually shifting to favour more moisture and more energy in severe weather events, is compounding two trends at once. The built environment is growing. The atmospheric environment is intensifying. The two trends multiply each other. And the next major piece of the picture is the climate shift that is about to arrive. By the second half of 2026, the Pacific Ocean is expected to complete its pivot out of La Nina and into El Niño, and that pivot will reshape American weather for the rest of the year. The signs are already visible in ocean data. Subsurface warming in the tropical Pacific has been accelerating. A large oceanic Kelvin wave has been moving east along the equator. Westerly wind bursts have been weakening the trade winds that previously kept cooler water in place. All of these are the precursors that precede an El Niño event. Forecast models suggest this El Niño could be a strong one. Some long-range analyses have raised the possibility that the event could reach what is informally called Super El Niño status by the end of the year, meaning sea surface temperatures in the key tropical Pacific regions run significantly above average. A strong El Niño would have wide consequences. It would reshape the jet stream. It would likely suppress Atlantic hurricane activity. It would bring wetter conditions to parts of the southern United States. It would bring drier conditions to parts of the north. And it would likely alter severe weather patterns in the second half of the year. El Niño tends to shift the jet stream south, pulling the northern storm track further south, and modifying the Gulf moisture patterns that feed severe storms. Historically, strong El Niño years have produced more active severe weather in some southern states while reducing activity in the Central Plains. The exact configuration varies, but the overall effect is a different map. That shift is not necessarily good news for anyone. A southward shift means the southeastern United States, including the Dixie Alley corridor, could see more active severe weather during fall and into early winter. A shift in moisture patterns could produce unusual severe weather in regions that have been quieter for several years. The country does not get safer as the ocean changes, it gets different. For tonight's storm, the El Niño transition is not the dominant factor. Tonight's storm is driven by the lingering La Niña pattern, the stuck jet stream, the warm Gulf, and the dry line. These are the ingredients of the current atmospheric configuration. The El Niño that is developing will take months to fully manifest in the atmosphere. The patterns shaping severe weather over the next few weeks are still largely the La Niña patterns. That means the next 6 weeks still matter. May is historically the peak month for severe weather in the United States. The jet stream configurations that have produced the front-loaded 2026 season could continue to produce active weather through May, before the El Niño transition begins to reshape things in June and beyond. Forecasters watching the long-range models are already identifying potential patterns for additional outbreaks in the coming weeks. The tornado count for the year will be largely set in the next 6 weeks. If the active pattern continues, 2026 could approach or exceed the recent benchmarks of previous years. If the pattern breaks earlier than expected, the season could end up closer to the long-range forecasts. Either way, viewers inside the severe weather corridor are not through the most active period yet, and as the season continues, there is one specific pattern on the weather maps that serves as a warning sign for the worst outbreaks. It is visible roughly 24 hours in advance. It is the kind of pattern that forecasters recognize immediately, and it is the kind of pattern that, when it appears, tells every experienced meteorologist that the next day is going to be dangerous. There is a specific pattern on the weather map that experienced forecasters recognize immediately as a warning sign of a major severe weather outbreak. It shows up roughly 24 hours before the outbreak itself. It has characteristic features that the models capture reliably. And when those features align, every experienced meteorologist in the country starts checking their preparations for the following day. The pattern has several components. The first is a deep trough in the jet stream dug into the western United States. A sharp trough with strong winds wrapping round its base is the engine that will drive the next day's severe weather. The deeper the trough, the stronger the upper-level support for storms. The second is a pronounced low-pressure system at the surface. A strong surface low, typically in the Central Plains, with a distinct warm front extending east and a cold front extending south, sets the stage for air mass collision. The area south of the warm front and east of the cold front, the warm sector, is where the severe weather will develop. The third is a strong low-level jet, a ribbon of fast wind close to the ground, typically pulling Gulf moisture north at highway speeds, feeds the warm sector with the fuel that severe storms need. When the low-level jet is forecast to strengthen into the evening and overnight hours, forecasters prepare for a long-duration event. The fourth is the dry line, a sharp moisture gradient across the southern plains, marking where dry desert air meets moist Gulf air, provides the trigger for initial storm development. When the dry line is forecast to sharpen during the day and push east as the atmosphere heats, supercells become likely. When all four of these features line up, the map looks unmistakable. Every experienced forecaster has seen it. The Storm Prediction Center's discussions describe it, the models depict it, and the warning goes out 24 to 36 hours in advance in the form of outlooks that raise the risk level across the corridor. For the public, this advance warning is the single most useful gift of modern meteorology. It is not perfect. The precise timing of storm initiation, the exact track of individual tornadoes, the specific towns that will be hit, these details remain uncertain until closer to the event, but the existence of the event, the general corridor, and the approximate strength of the atmosphere can all be known a full day ahead. That advanced knowledge saves lives. It gives emergency managers time to stage resources. It gives hospitals time to prepare for potential casualties. It gives residents time to identify their shelter locations and confirm their weather alert systems are working. It gives news stations time to communicate the risk to their audiences. In the Michigan case discussed earlier, the warning pattern did not fully manifest. The outbreak was smaller and more localized than the classic pattern. That is one reason the tornado watch was not issued. The atmospheric features that normally signal a major event were not all in place. Tonight's storm, by contrast, had the classic pattern visible more than 24 hours in advance. The Storm Prediction Center began raising risk levels days ahead. Forecast discussions described the pattern in detail. Emergency managers across the affected states were prepared. News stations communicated the risk. The warning system for this event had the lead time it needed. Whether every individual recipient of the warning takes the appropriate action is a separate question, and that is the part of the chain where the system hands off to the public. Every piece of the forecasting infrastructure can do its job, and the outcome still depends on what people decide to do with the warning. Which brings the story back to its most practical point. The difference between a severe weather event that kills people and one that does not, very often, comes down to a single unglamorous rule. A rule that works. A rule that is simple. A rule that is repeated every year by every forecaster, because every year people still ignore it. The single most effective action any person can take to survive severe weather is to be in the smallest, lowest, most interior room of a sturdy building when the storm arrives. That sentence contains everything. Smallest, lowest, most interior, sturdy. If you are in a site-built house with a basement, you go to the basement. If you are in a one-story home without a basement, you go to the bathroom or the closet in the center of the house, away from exterior walls. If you're in a commercial building, you go to an interior hallway on the lowest floor. If you're in a mobile home, you leave. Every weather service safety briefing repeats this. It is unglamorous. It is boring. It is repeated because it is the only thing that consistently works. A person in the correct shelter during an EF2 or even an EF3 tornado has a very high probability of survival, even if the house around them is heavily damaged. A person in the wrong location, even in a strong house, can be killed by a weaker tornado. The statistics on this are overwhelming. Survivors of major tornado events, when interviewed, describe the same pattern repeatedly. They were in a bathroom, or a closet, or a basement, or a storm shelter. The walls of that small room held when larger walls around them failed. Bathtubs, for reasons of structural geometry, have repeatedly been cited as survival locations. The plumbing anchors them. The small room protects them. People who die in tornadoes are disproportionately people who were not in the correct shelter. They were driving. They were in mobile homes. They were in large open rooms. They were near windows. They were outside. They were in garages or sheds. The location mattered more than the storm's strength. This reality is easy to state and difficult to internalize. Most people, when a tornado warning sounds, do something other than immediately go to shelter. They look out the window. They check the phone for more information. They try to confirm the threat. They ask family members if they heard it. They call someone. Each of those actions costs time. In a severe weather event, time is the resource that runs out. Forecasters have been pleading with the public about this for decades. When the warning comes, go. Shelter first, confirmation second. The warning system has already done the confirmation. It has already evaluated the radar data. It has already decided the threat is real. Your job, in the moment the warning arrives, is to execute the shelter plan, not to reevaluate the forecast. This is where personal preparation matters. Knowing in advance where your shelter is. Knowing how you will receive warnings, especially at night. Having a weather radio that alerts automatically. Having a plan for family members in different parts of the house. Having an alternative plan if you're away from home. None of this is glamorous. All of it saves lives. For tonight's storm, these rules apply as they do for any severe weather event. The corridor is large. The risk is real. The warnings will come probably before most storms arrive. What happens in the minutes after the warning is the part that is still up to the people inside the polygon. And as the 2026 season continues past tonight, the same rules will keep applying. The season does not end with this storm. The corridor does not close with this outbreak. The weeks ahead, through the peak of May, are the period when the most significant severe weather of the year is most likely to occur. Which leaves one final question. What does the rest of this season actually look like from here? The next storm is already forming behind this one. The 2026 severe weather season is far from over, and the most active month of the year lies directly ahead. May historically produces more tornadoes than any other month in the United States. The 30-year average for May runs around 300 tornadoes, making it the single most active month by a wide margin. April averages around 180. June averages around 200. May sits at the top. The 2026 pattern suggests May will not be gentle. Long-range forecasts from AccuWeather and other services have pointed to continued severe weather activity through the spring, with a corridor from the plains into the Mississippi Valley remaining active. The specific geography may shift. The traditional Plains Alley could become more active as the jet stream pattern evolves. The eastern corridor, including Illinois and the Mississippi Valley, could see continued events. Dixie Alley could activate if a southern track takes over. The honest answer is that the season is still unfolding. What forecasters can say with some confidence is that the ingredients have not gone away. The Gulf is still warm. The dry line is still active. The jet stream, while beginning to shift toward its El Niño configuration, is not yet in that configuration. The collision zone between cold continental air and warm Gulf air will continue to light up somewhere, and the question is mostly where. Storm tracks already visible on extended models hint at the next events. Bowing squall lines are forecast for the coming days across the southern plains. with the Storm Prediction Center already outlooking elevated severe weather risks for late this week and into the weekend. Supercell thunderstorms remain possible along the same corridor that tonight's storm is part of. The pattern, in short, is not breaking. For viewers inside the severe weather corridor, the practical meaning is continuity. Tonight's storm is one event in a sequence. The warnings that will be issued in the coming weeks will follow the same logic. The polygons will appear on the same parts of the map. The advice will be the same: shelter when the warning comes, leave mobile homes, stay off flooded roads, have a backup way to receive alerts at night. The season will end eventually. By mid-June, as El Niño begins to manifest more strongly, the severe weather pattern is expected to begin shifting. Activity in the Central Plains may decrease. The focus may move elsewhere. Hurricane season will begin in the Atlantic, replacing tornadoes as the dominant severe weather concern. The attention of the forecasting community will shift with it. But that is still weeks away. Between now and then, every storm system that develops across the central and eastern United States will be part of the ongoing 2026 story. Each one will test the warning system, the shelter habits, and the preparedness of the millions of people inside the corridor. Each one will add to the running totals that will define the season's final character, and each one will be, like tonight's storm, just one pulse in the larger pattern that the atmosphere has been producing for weeks. The deeper story is the one this series has been walking toward. The country has built itself into the path. The atmosphere has been loading its weapons unusually early. The warning system is working but stressed. The exposure is enormous and growing. The science is clear on most points and honestly uncertain on others, and the individual choices that people make in the minutes after a warning remain the final factor that determines outcomes. 40 million Americans under tonight's polygon. Millions more in the weeks ahead. A country that has spent a century building its cities and infrastructure into severe weather country and is now being tested by the pattern it inherited. The storm tonight is part of that test. So is the one forming behind it.